Hey everyone, welcome to Neural Notes, show where AI comes alive. Smash that subscribe button and ride the innovation wave.
You ever stop and wonder how something changes, not over a whole hour or even a second, but right now, in a single, fleeting instant? It sounds kind of impossible, right? But this idea is at the heart of so much of our world. So today, let's break down how we can actually measure a single moment of change.
Think about it. We all get the idea of average speed, right? It's just the total distance you traveled divided by the time it took. But a police officer's radar gun, that's different. How does it know how fast you're going at this very second? Not your average over the last mile, but your speed the exact moment that beam hits your car.
And yeah, this is the classic example that hits home for a lot of us. The officer shows you the reading, 56 miles per hour. That number, 56, isn't an average. It's what we call an instantaneous rate of change. So, how is that even possible? That is exactly the mystery we are going to solve.
Okay, so it all really boils down to two different ways of looking at change. On one side, you've got the average rate of change. Think of your total average speed on a long road trip. We measure this with something called a secant line. But on the other side, there's the instantaneous rate of change. That's the number on your speedometer right now. To capture that, we need a totally different and way more precise tool, the tangent line. And this is where it gets really cool, visually. The whole secret is seeing how we can magically transform the line for an average into the line for an instant. It all starts with two simple points on a curve. So just imagine a graph of your car's position over time. If we pick two different moments, let's call them P and Q, and then just draw a straight line connecting them, bam, you've got a secant line. The slope of that line is your average speed between those 2 points. Pretty straightforward, right? But here's the kicker. What if we don't care about the average between P and Q? What if we only want the speed right at point P? Well, let's do something interesting. Let's start sliding point Q along that curve, getting it closer and closer and closer to P. Just watch what happens to our line. See how it starts to pivot? And there it is, the big reveal. As Q gets so ridiculously close to P that they practically merge into one single point, our secant line completely transforms. It becomes the tangent line. This new line just barely skims the curve at that one single exact point. And guess what? Its slope is the instantaneous rate of change. That's the whole visual trick.
All right, seeing the line is one thing, but that's just a picture. How do we turn that picture into a hard number like that 56 miles per hour? We've got to find a way to calculate the slope of a line that, by its very definition, only touches our graph at a single point.
And you're probably thinking exactly this. The classic slope formula needs 2 points, right? But a tangent line only gives us 1. So what do? We use the same trick as before, but this time with numbers. We're going to sneak up on the answer. Let's say we want to find the exact slope at x equals 2. Now, just look at this table. We're calculating the average slope between points that are incredibly close to 2. See what happens when we come at it from the left side. With 1.9 and then 1.99, the slope gets closer and closer to a specific number. And check it out. The same thing happens from the right, coming from 2.1, then 2.01. It's like both sides are squeezing in on the real answer.
And that number is 4. The slopes from the left are getting closer and closer, 3.9, 3.99. The slopes from the right are also zeroing in, 4.1, 4.01. I think we can all agree the only logical conclusion is that the slope of the tangent line at that exact instant, x equals 2, has to be 4. We found our number.
Now, this isn't just some abstract math trick. It is fundamental to how we understand the universe. So let's take this idea and apply it to a real-world, or I guess an off-world problem. Let's see how this all works for a rock thrown on Mars.
Okay, here's the setup. We have a formula that tells us the exact height of a rock on Mars at any time, t, and our mission, should we choose to accept it, is to find its velocity, its instantaneous rate of change at the precise moment it's been in the air for exactly 1 second.
So our game plan is to sort of box in the answer. First, we'll calculate the rock's average speed in the full second before our target time. So that's the interval from 0 to 1 seconds. Turns out that's 8 meters per second. Next, we'll do the same thing for the second after our target, from 1 to 2, and that one comes out to 4 meters per second.
So as you can see right here, we've trapped our answer. The true speed right at t equals 1 has to be somewhere between the average speed just before it, which was 8, and the average speed just after it, which was 4. So a really good first guess would be to just, well, average those two numbers.
And that gives us a fantastic approximation. The average of 8 and 4 is 6, so we can say with some confidence that at the exact instant t equals 1 second, that rock was cruising upwards at about 6 meters per second. We just calculated the velocity of a rock on another planet at a single moment in time. How cool is that? Oh, and one last super important point. The units you use always follow a really simple rule. It's just the units of your vertical axis per the units of your horizontal axis. That's it. So for distance over time, you get miles per hour or meters per second. If we were tracking money over time, it could be dollars per year. It works for everything. So, what's the big takeaway here? We've learned that to measure change at one specific moment, you can picture it as a tangent line, and you can calculate it by looking at the average change over smaller and smaller intervals. And trust me, this idea isn't just for speeding tickets or rocks on Mars. It is a cornerstone of physics, engineering, economics, you name it.
And that really leaves us with one final thought to chew on. Now that you know it's actually possible to precisely measure the rate of change at any single moment, just think about what that means. What other seemingly impossible questions about how the world works could you now start to answer?